Hi everyone, in this chapter we are going to talk about chemical equilibrium. To understand this chapter clearly, you should be familiar with the previous chapters, which is energy in chemical reactions and rate in chemical reactions. Okay, let's start. First, define the chemical equilibrium. The composition of calcium carbonate in a closed container is given as calcium carbonate solid decomposed with heat here to produce calcium oxide solid plus carbon dioxide gas. Now this occurs firstly. Now after a while, this reaction turns vice versa. It becomes as calcium oxide solid combining with the carbon dioxide gas to produce calcium carbonate solid. Now the first reaction was endothermic. When you change the reaction, just remember Hess law, it becomes exothermic. And the moment comes, forward and reverse reaction rates becomes equal. So the reaction reaches equilibrium. So this is the definition of equilibrium. When forward reaction and reverse reaction rates become equal, the reaction is said to be at equilibrium, and which is also called as dynamic equilibrium. Now dynamic means the reaction never stops. So it goes forward, then after a while it comes just reverse. So it's called as a dynamic equilibrium. Now on, you can use the equilibrium sign like this. Calcium carbonate is at equilibrium with its products, calcium oxide solid and carbon dioxide gas. Now, what are the properties of this equilibrium? Now, this is an example of a chemical equilibrium. So there's a decomposition reaction. But if I tell you that some water molecule is at equilibrium with this vapor pressure, then this is said to be a physical equilibrium. Now let me give a reaction. This is the nitrogen tetroxide. It's decomposed into nitrogen dioxide. So what can be their graphics in terms of their molarities and their rates? Let's say that this is the molarity graphic, and you have time here. This is rate graphic. Again, you have time here. Now, when you start the reaction with the nitrogen tetroxide, this means that initially the forward reaction is really fast. So after a while, the forward reaction just decreases like this, and reverse reaction rate increases like this. So at time t here, they're going to reach equilibrium. This is rate forward and this is rate reverse. So this is the moment of equilibrium. And in fact, also this graphic shows the definition of equilibrium. Now, what about the molarities? Let's say that you have 2 molar of the nitrogen tetroxide in the beginning and you have no nitrogen dioxide. And again, in this chapter also, you're going to use the stoichiometric calculations like we have done before. Let's say that only the 50% of this nitrogen tetroxide is decomposed to produce twice its amount of 1 molar here, and which is 2 molar of nitrogen dioxide. So what would the graphic look like? You have the nitrogen tetroxide here. It started from 2 molar, and after a while it decreases to 1 molar here. This is 1 molar. Now, what about nitrogen dioxide? When 1 molar of the nitrogen tetroxide is decomposed, it is going to produce 2 molar of nitrogen dioxide in the same time interval, and it goes like this. Now, this is the moment of equilibrium. Now, as you see in this reaction also, there is no 100% yield. The yield is really low. For all the equilibrium reactions, the yield percentage probably will be asked. Now at equilibrium, observable reactions stop, but unobservable reactions continue. That's why we call this equilibrium as the dynamic equilibrium. Concentration of reactants and products are constant. Just be careful, they are not equal, but they are constant. Reactants are never finished. Now I put a sign here. On some occasions, reactants are going to be consumed totally. I'm going to give you an example later. And during equilibrium, temperature should be constant. This is very important. Now, if rate of forward and rate of reverse reactions are equal, let's remember the reaction. The nitrogen tetroxide, it is decomposed into 2 nitrogen dioxides. Rate of forward reaction is equal to rate of reverse reaction. Now, what about their rate laws? So, for the first one, rate forward, K forward times the nitrogen tetroxide's concentrations equal to, and K reverse times nitrogen dioxide concentration square. Just when you gather all these rate laws, rate constants, on the left hand side, it's going to be like Kf over Kr is equal to nitrogen dioxide's concentration square over the nitrogen tetroxide. So this value gives you Kc here, which means equilibrium constant in terms of concentration. So in order to find that Kc, you have two formulas. You can rather take the Kf over Kr, or you can have the nitrogen dioxide squares, concentration squares over the nitrogen tetroxide concentration. So this is products over reactants. Equilibrium constant with pressure Kp can be calculated by using the partial pressures of gases in the reaction. If you like the Kp for that decomposition reactions, it's going to be like pressure of nitrogen dioxide square over pressure of the nitrogen tetroxide. Or in some occasions, you're going to be given the value of Kc only, and you will be asked to find the value of Kp. In this case, you have a formula. Kp is equal to Kc times RT to the power of delta N. That delta N represents products in gas phase minus reactants in gas phase. Their coefficients, in fact. Now, for this example, your delta N, remember the reaction. Delta N is equal to 1 here, coming from 2 minus 1. Now, problems and calculations based on equilibrium constant. Let's start with an easy example. You have 2A gas plus 1B solid. Remember, just be careful, this is solid. They give 3 carbon 3C or solid. If the molarity of A is 0.01 molar at equilibrium, what about the equilibrium constant? Now just remember, these are solids. As in rate, also in equilibrium, solids and liquids are not encountered, so you just skip them over. So it's going to be like, if there is nothing to be written on the right hand side, you're going to put 1 here over A's molarity square, which will be 1 over 0.01 to the square to the power of 2 here, This will give you 10 to the power of 4. If the unit is asked, it's going to be 1 over molar square. Next question. You have hydrogen gas plus X2 gas. They combine to give 2 hydrogen X gas. Now you have 1 liter vessel and you're starting with 0.1 mole of each gas. So you have 0.1 molar of hydrogen and 0.1 molar of X2 gas. So it says the equilibrium constant in terms of molarity is 9 here. So what about equilibrium concentrations? Now here is my initial values. Then there's going to be some reaction. And what about at equilibrium? Now remember, equilibrium reactions were not 100% yield reactions. So you cannot say that 0.2 molar of hydrogen X is produced. This is not correct. Please erase this one. Now it's going to be like this. If you just consume X molar of hydrogen and X molar of X2 gas, then 2X molar of hydrogen X is produced. So finally, at equilibrium, you have 0.1 molar minus X of hydrogen, the same amount of X2, and you have 2X of hydrogen X here. Now, if this is the equilibrium values, now you can equalize them to equilibrium constant, which will be 9 is equal to 2x squared over 0.1 minus x squared. So you're going to take the root of everywhere. Then will be 3 is equal to 2x over 0.1 minus x. So 0.3 minus 3x will be equal to 2x. So 0.3 is equal to 5x. You're going to find x as 0.06 molar. So if the equilibrium concentrations is asked, please do not forget to write x in its place in the equilibrium. So this is going to be, the answers will be 0.04 molar, also 0.04 molar, and this will be 0.12 molar. Now you can just check yourself, just do the products over reactants, and you will see that this is really equal to 9 here. Now relation between the chemical reactions and Kc. Now remember Hess law. When you're using the Hess law, you could just multiply the reaction by 2, then you were multiplying the delta H value by 2 also. So when you are just changing the reaction vice versa, you were just taking the minus sign of the delta H. So when you're calculating delta H, you were just subtracting the molar heat of reactions, molar heat of formation of reactants from the molar heat of formation of products. So in this case, you have a dividing here. It's going to be like this. When you change this reaction all over again, you're going to take the x to the power of minus 1. It's going to be 1 over x here. So it was products over reactants, then it becomes reactants over products. So you're just taking the 1 over that Kc value. If you multiply by 2, in this case, you're going to take the square. If you're taking the half of it, you're going to write it as x to the power of 1 over 2, or in root of x here. So if you really use the Hess law, when you just sum these reactions side by side, C's are just simplified here, and you're ending up with 3a plus 3b will giving you 2d here. So nu k. In Hess law, you were just all summing these delta H values up. In this case, you're going to multiply them. K1 times K2 times K3. Reaction quotient. Reaction quotient is shown with Q here. And it is the value of, again, products over reactants. Again, you're not taking the solids and the liquids, only the gas phase and aqueous phases. And this is the value of product over reactants at any time. It cannot be equilibrium, and probably it's not going to be at equilibrium. Then you compare it to Kc to understand whether the reaction is at equilibrium or not. And if not, decide which direction the reaction favors. For example, if the QC is equal to Kc, this means that the reaction is at equilibrium. So it doesn't favor any side. But if QC is higher than Kc, let's say that you have found the QC as 10 here and Kc was 9. This means that you should just decrease that 10 to 9 here, meaning decreasing the concentration of the products and increasing the concentration of reactants. So this means that the reaction favors reactants. If the value is smaller than Kc, so in this case, this means that you need to have more products increasing in order to increase that value. And in this case, the reaction favors products. Now, this is the last part of this chapter, the factors that affect equilibrium, Le Chatelier principles. When a reaction at equilibrium is disturbed by a change, which can be amount of reactant or product, it can be volume, it can be pressure, or it can be temperature. The reaction will give a response to that disturbing. This is called Le Chatelier principles. For example, the decomposition of ammonia reaction is given and you add some nitrogen into the container. Now initially there is equilibrium. So here is the concentrations and here is the time. When you add some nitrogen to that container, the reaction will likely consume a little bit of that nitrogen and it's going to favor reactant sides, where the amount of hydrogen is decreased, where the amount of ammonia is going to be increased. Now, what about their graphics? Let's say that this is nitrogen here, this is hydrogen here, and this is ammonia here. First, you have to show that they are at equilibrium initially, so you're going to draw straight lines. Then you're going to show your effect on the reaction. You add some nitrogen here, so here is the added nitrogen. It's going to be like this. Then you're going to show the response. Then the reaction just goes left-hand side, meaning the ammonia is increased, where the hydrogen is decreased. The nitrogen will be consumed a little bit, but its concentration will be higher from its original value. So this should be the new equilibrium. This is the equilibrium 1, let's say, and this is new equilibrium. Change in volume and pressure. When volume increases, meaning the pressure decreases. Also, this means a decrease in the molarity. The equilibrium should favor the side where it has higher number of gas molecules. But if the vice versa is done, if the volume is decreased, meaning the pressure is increased and the molarity is increased also, the equilibrium should favor the side where it has smaller number of gas molecules. So let's look at this one. Now it says the pressure is increased. Now this means that volume is decreased and also means that molarity is increased. So here is my graphic, molarity versus time graphic. Let's say that this is nitrogen, this is hydrogen, and this is ammonia. I'm just making them up, writing in whatever order I like, so you can just do the same thing. First, they are at equilibrium. Please just draw the straight lines. Then show the effect that you have done. the effect that you have done was decreasing the volume, so increasing the molarity of each gas like this. So what about the response of the reaction? Now if have smaller volume, this means that the reaction favors the side that has a smaller number of gas molecules. Now on the left hand side you have 2 molecules, on the right hand side 4 molecules, so it goes to left, favors reactant side. So what will happen? Hydrogen and nitrogen is going to be decreased, but will be higher than the initial value, and ammonia was increased by the help of the decreasing in volume, and because that it favors the reactant side, it will increase more. So it doesn't matter which side the reaction favors. When you decrease the volume, molarities of all the reactants and the products in gas phase increases. This is very important. This is equilibrium and this is new equilibrium. Change in temperature. Now change in temperature, let me put a star here. This is very important because temperature is the only factor that affects Kc. For example, when the temperature is increased, this means that the kinetic energy is increased. The reaction should consume that kinetic energy a little bit. So the reaction will favor right hand side because the delta H on the left hand side. So when you draw the graphic, molarity versus time graphic, again I'm just writing the same order. It just goes like this first at equilibrium. Then the reaction favored product side. There is no, again, remember the straight lines here, just going upwards or downwards, because you do not just play with the volume, play with the molarity or the amount of substance. You only play with the disturb the temperature. So you just directly show the response here. It goes right hand side, so nitrogen just increases like this, hydrogen increases also, and ammonia decreases. And this is the reason why the temperature is only the factor that affects Kc. Let's summarize this information. Only temperature affects Kc. So when temperature is increased and if the reaction is endothermic, then the value of Kc becomes higher. But if the temperature again is increased and the reaction is exothermic, then value of Kc becomes smaller. So this is very, very, very important. So what about adding catalysts? Catalyst has no effect on equilibrium. It just makes quicker for the reaction come to equilibrium.